This is the second half of the bonding properties video. This is basically for covalent only, and this is talking about network solids, allotropes, and isomers. So a network solid is really simple. It's when all the atoms are bonded together in a network. And so everything is covalently bonded to itself. If you look at these on the bottom, these are examples of network solids. I have some model kits that I can show you in person about network solids. But here's the idea. Since all the molecules are covalently bonded together, and covalent bonds are pretty strong, these things are like indestructible. They have incredibly high melting points, some of the highest in the world or in the universe. They are very hard, some of the hardest materials in the universe, and because they're all interconnected, they're not going to break up if you try to dissolve them in water the way a salt would, or the way certain molecules can dissolve in water very easily. These guys are not. And the reason is simple. Because of their interconnectedness with covalent bonds, you need to break all the bonds in order to melt or dissolve it or break it. A couple examples of this, if you haven't already figured it out. Graphite, the stuff you write with. Now, a lot of people may call me on that and say, hey, I thought graphite was, some of the hardest material on Earth, but if I use it in my pencil and it breaks off, then how is it really that hard? I'll explain that. Diamond and silicon carbide, which is basically fake diamond. It's just not shiny and so therefore not as valuable. So back to the graphite question, why is graphite a network solid? Is because if you look at graphite, graphite's actually this one right here. It's layered. And so when you write with a pencil, you're actually shaving off layers of graphite. You're not breaking the bonds within the graphite. If you tried to break the bonds inside of the graphite, that's a different story. That would be much harder to do. But to just shave off a thin little layer and get that layer to shake off onto your paper when you're writing with a pencil, that's not so hard. And so obviously not all network solids are created equal. So last thing I need to mention is the difference between an allotrope and an isomer. So in chemistry, they love to come up with names for things. Turns out allotropes and isomers are basically the same thing. They're just slightly different. An allotrope is when we have the same element with a different structure and therefore different properties. These are all allotropes. The reason they are allotropes is because they are all made of pure carbon. So you can have coal, diamond. This fancy ball thing is called a Buckminster fullerene. That's two German scientists' last name together. They're the ones who discovered it. Carbon nanotubes, which are these tubes of carbon, and graphite, which we talked to, and I don't even know what this thing is down here, but it's enormous. And so these are all allotropes because they are the same element, but they have different structures. The different structures cause different properties. Do not confuse that with an isomer. An isomer is almost the exact same thing. The only difference is an isomer is when a compound does it. So when a compound has different structures and different properties, we call it an isomer. When an element does it, we call it an allotrope. So be very, very careful there. They're basically the same definition. That is literally the only difference. It's like, I'm trying to think of another example, and I'm sure I will. Maybe like atom and molecule. If it's a single element, we call it an atom. If it's two or more, we call it a molecule. That's not the best definition because some elements are molecules, so that doesn't really work. But you get the idea. These are very, very similar definitions. They're just being particular in saying, okay, when an element does it, allotrope. When a compound does it, which is two or more different elements combined, then we call it an isomer. So that concludes these notes.